The sort of electrons will flow backwards and forwards through it, but not just pass right through like a sort of short circuit. So to describe the capacitor, to actually show you what a capacitor does, let's make one. So I've got a bit of cardboard here. This is a standard 6x4 photo piece of photo material. And I've got 2 bits of metallized film. So let's stick the metallized film on either side. So we've got a metal electrode, and I'm sticking it onto the insulator, the dielectric. And this is old aluminium tape, I think, because it doesn't seem to stick very well. But that's alright, it'll do what we need to do. And then the other side of this, I'll stick the other bit of tape, and that's the other electrode. And this is the physical construction that's used throughout all capacitors. They're all pretty much like this, but not using cardboard and aluminium foil. So let's get that pretty much as close to the other one alignment as possible. And the 2 factors determining the capacitance here are the area of metallization that's in parallel with the other one, and how thick the insulator is in between. And you'd think, you know, this card, it's very thin, so it's going to be quite it's going to be a modestly high value of capacitance, but that's not true. This is not going to be a high value of capacitance at all. So let's put this round, let's be optimistic and say 200 nanofarad. And I'll connect it one side and the other side, and the capacitance is actually, I'm actually connecting onto the adhesive side here. My capacitor measures oh, that's terrible, isn't it? It's 1.8 nanofarad. It's not very high at all. And if I was to cut this in half, so the actual, to prove that the area of the foil affects the capacitance, if I get a pair of scissors, and I cut this in half right now, so it's 1.83, if I cut that in half, it's half the capacitance, it's now 0.8, and if I cut that again in half, it'll go down to about 0.4, which it has. So that's basically how a capacitor works. It's basically an insulator, the 2 metal plates on either side, and the area of the metallization and the thinness of the separator is what determines the capacitance. And to get the value of capacitance up, that means that in reality, for components like this little 100, keep in mind that I managed, what was that, just a couple of nanofarad? This one is rated 100 nanofarad. And if you look at things like this, this is an electrolytic capacitor which is rated 470 microfarad, which is a massive capacitance. And to achieve that, let's get the notepad back in again. To achieve the higher capacitance, they often make the capacitors multi-layer. So this is something I just printed out, designed it on the computer for the printed circuit board design sort of layout, but I just did it as a sort of graphic. And if you can imagine that the blue is layers of insulation in the ceramic capacitors, and these are metallized sort of plates, then by alternating the pole, sort of creating a sort of comb of them with insulators, and then putting a metallization down the end to connect them all together, you can create quite a large capacitance in a small area just by making it a multi-story capacitor, so to speak. And that's still the layers of insulation in these, it's still going to be super thin. You'd need a microscope probably to see all the layers. Where you're going for a high voltage capacitor, the size has to go up. These are also 100 nanofarad. So you look at this one, it's 100 nanofarad, it's really small, but it's a low voltage one. When you're increasing the voltage, you have to increase the thickness of the dielectric, the insulation between them. And to make this type of capacitor, these are metallized film capacitors, and it's a film that's metallized on one side. And they take 2 strips of it, and they basically sandwich them together. And the plastic aspect of it is the insulator, and the metallization is the electrode. And to fit a lot in a small area, they then actually just spiral. They take a big long strip and they spiral it round into a small area, and that's what creates the sort of larger area. And the thickness of the plastic film itself will determine the voltage rating. This is a ceramic disc capacitor, usually quite low values. It's usually one of the simplest, and it usually is just a disc of ceramic with a conductive layer on both sides, and then an electrode that just comes across and comes off, and then it's dipped in insulation. But when you think that even this one is rated 10 nanofarad, and it's rated 1000 volts, but to get that 10 nanofarad, the insulation must be really, really thin inside that. I've never actually opened one of these up. Let's open one of them up right now and take a look. Oh, not this thing to do with your snips. Oh, that is so... it really is wafer thin in there. It's so thin that most of the thickness of that is the protective coating. That is super thin in there. I don't know if you can even see that. It just looks like a line. So, electrolytic capacitors are one of the more exciting capacitors, and I don't mean that in a good way. The electrolytic capacitors, to achieve such a high capacitance, they contain a liquid electrolyte. And they have a very thin foil inside. And the foil, to create an extremely thin insulator, they form an oxide layer on the aluminium foil in there. And that means it really is like micron thick, which means that they can get a very high capacitance in a small area. But to couple onto that surface, they have to use a liquid electrolyte, which then, because if you looked at the foil, it would look all pitted and mottled with that oxide coating. So to get a good coupling, they use a liquid that just fills in those gaps. And that's one of the downsides of, well, it's many of the downsides of the electrolytic capacitor. Because traditionally, all the old, say for instance, all the old video games from the 80s tend to suffer problems after a while with what's called drying out of the electrolytics. They still measure the correct the capacitance, but their equivalence of resistance, the resistance to current flow through them changes, it increases. And what that means is that they stop doing their job properly. In when you get the large values like this, they're usually used to smooth ripples. So say for instance you had the output from the mains was rectified, and you had a big peaky sort of like the AC full wave rectified AC waveform, which is like the two sides of a sine wave. Then by putting this across that, it then just creates it reduces it to a very slight ripple and a nice smooth DC voltage. And as that capacitor dries out over time, that ripple will get bigger, and it ultimately starts causing problems when it dips down so low that the electronics can't sustain normal operation. And that's when you have to change capacitors. However, that's more of an issue with modern electronics, because whereas in the old days these capacitors only had to deal with like 100 Hz or 120 Hz, just mains frequency rectified. Nowadays the capacitors have to deal with the output from switch mode power supplies, which is like thousands of hertz, tens of thousands of hertz, and it means that they actually heat up and they dissipate more energy. They're put under a lot more stress. And if you look at the top of this one, you'll see there's a little cross on it, and that's a safety vent, because when these fail, what actually happens is that oxide coating can be perforated, and that's really common if you accidentally connect them in reverse, because it relies on the polarity to keep that oxide coating intact. When you connect them in reverse, that fails, and then suddenly you've basically got this liquid-filled thing just connected across the power supply with no current limiting it. Just basically it turns into sort of resistor, and it boils the electrolyte. And when that happens, the top will either sort of, if you looked at from the side, it would bulge up. But if it goes too far, that X that's etched onto the top will split open and it will vent out the top. And the other option there, if it doesn't do that, is sometimes it blows the whole can off, and it just makes a mess. It gives out a vapour of the electrolyte, which is slightly caustic. It can unravel the foil across the room. It can go off with enough force to actually cause injury if it hits you. So you have to be kind of careful with electrolytic capacitors. So what do we cover? Let's look at diodes now. Diodes come in various flavours. They're used for various functions. You get signal diodes, rectifier diodes, and light emitting diodes. The function of a diode is to allow current to flow in one direction but not the other. So the symbol for a diode, I didn't mention the symbol for a capacitor was that, basically representing the two metal plates with a sort of air gap in between. And the case of the electrolytic, that has the positive and negative are marked with the positive being the sort of just the empty box and the negative being the sort of filled box, just for the polarity reference. However, moving on to the diodes, the symbol for a diode is very easy. It's very self-explanatory. In the water equivalence thing, it would be a pipe with a one-way valve in it, so the water could only flow one way. In this case, you have the anode of the diode and the cathode, spelt with a K. I'm not sure why they do that. There must be some reason. I've never really investigated that too much. But current will flow positive from the anode. It will flow through the diode to the negative. But if you try reversing the polarity, very little current, if any, will flow through that diode in reverse. And the main values you have to consider with diodes are the current you want to flow through them. Say, for instance, this is a 1 amp diode. It's rated to handle 1 amp flowing through it. Something like a 1N4148 signal diode. It's not designed for anything major. It's just designed for, say, rectifying small electrical signals. So it's only rated about 100 milliamps or so, if that. And the other factor is the peak inverse voltage. That's what sort of voltage it will block coming in the wrong direction. So supposing if you did connect, well, this one is a 1N4007, it's rated 1000 volts. So that means that it will block 1000 volts going the wrong direction. But if you were to exceed that dramatically, it will avalanche and it will start conducting the opposite direction. So you have to choose the correct diode for the job. This is a silicon diode, which typically has when it's forward passing current in the correct direction, positive to negative, it will typically have a voltage drop of about 0.6 volts. Sometimes, it depends on the voltage rating. It'll actually sometimes go up to 1 volt, and it also depends on the current flowing through it. You get Schottky diodes, which have a much lower forward voltage of between 0.2 to 0.5 volts, and in cases of rectification, that lower voltage actually makes them much more efficient.